Hey there folks, and welcome to this presentation on modernizing Amazon.com warehouse device connections with AWS IoT. I am Rudy Chetty, a solutions architect with AWS, and I'll be joined by Avi Dubey, who's a senior software development engineer with Amazon later in this presentation. But let's get going. So the agenda for today, we're going to go over the AWS IoT core. We'll do AWS IoT Greengrass, then touch upon FreeRTOS, and then we'll bring up our customer Avi to talk about the solution that they've implemented using these technologies. So let's get going. So with the AWS IoT core, it is the crux of the AWS IoT platform. And we start with all the features that it comes with. The first one being the identity service. So we've got these devices that need to connect into the AWS IoT core, and they want to do it in an authenticated manner, or they want to be authorized as well. So we use certificates. These are X509 industry standard certificates, and we allow you to use your own ones, so you don't even have to provision AWS certs. So if you have your own mechanism that vends certificates, you can bring your own certificates to the table. Or if you prefer the managed approach, you can use AWS vended certificates. You can do them in a manual fashion, so you can provision per device. So that means installing a certificate on a device, each device that you have in the field. Or better yet, you can do it in an automated fashion, or just-in-time registration, which is JITR. What that means is at manufacture time, you get the vendor to install certificates on the devices, and by the time that they go out to their end users or customers, the certificates have been registered in the background with AWS, so that when those devices turn on, they actually connect to the AWS IoT core right out of the box. Other forms of connection or authentication is signature version 4, even token-based authentication. And once you've connected the devices, you want to make sure that they have the authorization to perform certain actions, such as sending a message, subscribing to a topic, and this is where IoT policies come in. They're very similar to IAM, or Identity and Access Management policies, and they allow you to create JSON documents that determine whether you allow or deny certain actions. Better yet, if you want to separate your infrastructure users between your end users, you can do that. And you can use Amazon Cognito, which allows you to provision users separately. So you keep all your infrastructure users in IAM, and then you keep your end users in Amazon Cognito. And you can federate to existing identity stores if you have them, or you can use Cognito as your identity provider. The next feature we want to talk about is the device gateway. So we've connected our device, and now we're thinking, well, we want to make sure that we can send messages between the two. So we set up what we call bidirectional long-lived connections. So that means we can send data to the device, and the device can send data to us, and us being the cloud. It's done via MQTT, WebSockets, or HTTP. And MQTT here being messaging, queuing, telemetry transport. It's a much smaller payload than HTTP, and it allows you to stream updates a lot faster, I'd say. It's using the industry standard TLS 1.2, so if you have devices that are using the older version, it's kind of recommended to upgrade them to the more recent 1.2. And we're operating on constrained devices, so the device gateway actually allows you to, to provision those devices and still keep them connected to your device gateway. The next one is the message broker. So we've connected our device, we're sending messages, but now we want to think, okay, well, which messages do we want to send and where do we want to send them to? So what you actually end up using is a publish-subscribe model. So you use topics, and these topics you send one message to by publishing it to it, and then from there you can have multiple subscribers, which through one message you fan out to multiple subscribers. That's a one-to-many relationship. So it's an easy way of hitting multiple devices in one go. And as I mentioned, it's using topics. Now these topics can be reserved, so ones that come out of the box when you provision an actual device, and they start with $AWS. You can even use custom topics. So if you want to provision certain ones based on your requirements, you can do that along with wildcards. So say if we want to turn off all the lights on a floor, we could use a custom topic, or we could even use a wildcard to say, execute this particular action against all the lights on a particular floor. We also support offline queuing. And what that means is messages that go through and say the device is offline, they can still propagate once the device comes back online. And you don't lose those messages because the device was offline itself. And QoS, this stands for quality of service. We support 0 and 1, which means a message is delivered 0 or more times, and 1 being 1 or more times. There is support for QoS too, but it's kind of in a different feature called the device shadow, which we'll touch upon later. Now the rules engine. Again, we're sending messages. They're going from our device to the AWS IoT core, and now we want to route them accordingly. And you make use of rules, which is a data transformation paired with an action. Now, the data transformation part is kind of familiar to most people. It's using SQL-like language. So for an example here, we're selecting star, so wildcard, from a topic /XYZ, where the temperature is greater than 35. Now, in this case, it could be 35 Celsius, Fahrenheit. We can actually go further and say, if it is one and we want to convert it to the other, so say it was Fahrenheit, we can enrich that data. And we can use mathematical functions that are built in, even string manipulation and date manipulation too. And what that does is you can run Lambda functions against those pieces of data that are coming in and convert them accordingly depending on your need. Maybe you even want to add geolocation. You can tag that using Lambda functions. And once you're ready with the data that you've transformed, you pair it with an action. Now, with the action, you can actually send the data to existing AWS services right out of the box, or better yet, you can even send them to third party. And you see we've listed quite a few of them here on the right. IoT Analytics, we've got S3, and then Salesforce in here. So you can route them with rules that are built into the AWS IoT core engine. And one of the last things to touch upon before, actually, it's not one of the last things, the second to last thing is to talk about the device shadow. Now, device shadow is a logical representation of device state. What that means is it's a fancy way of saying we've got a JSON document that manages the state of your device on the cloud. Now, you can see here we've got a desired field, reported as well, and these are pretty important in the sense that the reported is what your device is reporting to the cloud. So say if in this case we've got latitude and longitude being specified, and maybe we're thinking, okay, it gets to the cloud, but it's the wrong latitude. Now, if we want to change that, we use the desired field. So we set that on the cloud, and that propagates back to the device. It also supports offline queuing via SDKs and API. So again, you don't lose those state changes that happen in between the device going offline and coming back online. But it's kind of usually better to illustrate this with an example. So let's jump into that. So in this example, we've got a fan. The fan's got a shadow. And then on the left, we've got, or is it the right? On the right, we've got an application. Now, this application is registering data or checking on what's happening with the fan. In this case, it's reporting that there's an LED, and that LED is blue, and that goes to the shadow. So when the application queries it, it says, what's the current color? It's going to be blue. But, we're feeling in one of those moods. Maybe we're a bit emo today, and we want to set it to red. So we say, okay, let's set the desired state to red. But it's offline. Are we going to lose it? No, we won't. We'll keep that state change, and when the device comes back online, gets set to red. And then the last step there is that it reports back to the AWS IoT device shadow that it has registered the change. That means when your application queries it, at step number 6, it'll show red. Now, as I mentioned, the last thing to touch upon here is the registry. And most people start with 1 or 2 devices. They go 3, 4, maybe 10, and then they realize, this is kind of getting unmanageable from a searching perspective. So we introduced the AWS IoT Core's device registry, which stores static metadata about devices. So whether that's manufacturer, serial number, it's a way of you easily searching through your numerous amount of devices. Now, you can group them into what we call thing types. So I mentioned the example of light bulbs. We could go through our devices and say, let's designate certain ones to be light bulbs. That means is if we need to run anything against them, we can run it against a thing type called light bulb versus using a wildcard. We can go further and actually group them. So again, if we stick with that light bulb example, I said, let's group all the light bulbs on floor 2. So we could do that using groups, and then we write one job and we run it against these groups. And it's a way of doing it without writing, say, a glorified for loop to actually go through each and every light bulb on that floor to turn them off. So that's the AWS IoT core. Now, customers, we listen to feedback that you provide to us, and we kind of adopt and develop products in response. And one of them was, we really like the AWS IoT core, but we want to have some way of having that same functionality brought to the edge. This is where we introduced AWS IoT Greengrass. The first thing to talk about with Greengrass is local messages and triggers. So if we have two things that need to communicate with each other apart from using the cloud, they can go through a Greengrass core. In this case, thing A is sending a message through the core and it's being received by thing B. Another feature is local actions. What this means is, say the temperature in thing A spikes to an undesirable temperature, we can have a fan turn on to kind of mitigate that. So the way that happens is a message is sent to the core, a Lambda function is run, and in response, the fan turns on. You also get data and state sync. This means that you can constantly send data to your core, and maybe late at night you're thinking, well, this is the best time to actually sync. Then you can sync to the AWS IoT Core Cloud to actually have your data be registered once versus multiple times a day. It's the same security that you're used to with AWS grade security here being TLS 1.2, encryption as well. So all your links are secured. You even have local resource access. So if you have a hard drive connected, you can access data on it or write to it through your Greengrass core. You even have access to GPIO pins. So if you have low-level sensors connected, you can perform actions in there or maybe even read data from it. And machine learning. This is an area that people really like to explore, and we give you that capability by allowing you to train models using Amazon SageMaker. Then you can export them and run them on your Greengrass core using machine learning inference. Better yet, if you have a GPU or graphics processing unit connected, you can make use of that as well because it's connected to the core, and as we mentioned, local resource access is granted. One other thing to note is that connectors come out of the box. Whether these are third-party like ServiceNow or Twilio, you also have access to certain services like S3, AWS IoT Analytics, and right out of the box you can connect from your AWS IoT Greengrass core to those services, or you can use the connectors to actually pull data from devices that you might not be able to in the past. And over-the-air updates, that's one of the final things to touch on here is you have updates that come through. If those of you who have smartphones, you've probably seen it where it says update available and click here whether you want to install or decline. It's a similar premise here where you send an update from the AWS IoT core to the device and the device will install it. And if everything goes to plan, you get the A-OK. But if it doesn't, you have failover that's built in, so you can roll back to the previous version, hopefully not brick your device. Now that's the AWS IoT Greengrass service. The one final thing I'd like to touch upon is Amazon FreeRTOS. Now, Amazon FreeRTOS came about through an acquisition, and there's two different versions. There's the community version and then the Amazon flavored version, which has all these unique features built in, and it's a modular architecture. So you've got the hardware that you're going to run it on, you've got the next layer here, and you've even got the libraries that start piling up and building onto it, such as the MQTT agent, you've got the shadow library and so forth. And this is how the architecture can be built, and you can utilize features as needed. You don't have to utilize the whole stack. So what comes out of it? You've got the local connectivity libraries. What that means is you have access to edge gateways, you can have access to Wi-Fi access points, even AWS IoT Greengrass connectivity comes right out of the box with Amazon FreeRTOS, so you don't have to go in and implement that yourself and do that heavy lifting. You also get Wi-Fi management, so if you had several connections or you want to manage credentials, you can do that using Amazon FreeRTOS. You even have access to Bluetooth Low Energy. So if you want to connect to Bluetooth devices, you can do that using the service. You have iOS and Android SDKs that are available. So if you want to develop for either of those platforms, you can utilize Amazon FreeRTOS. And you know what? We have the same kind of offline queuing, if you want to think about it, where if there's no cloud, no problem. You still have access to your local libraries, and you could route messages over an AWS IoT Greengrass core or so forth. And then you see you get the more of the Amazon flavor here with the cloud connectivity libraries. And what that means is if you've got AWS IoT core, you can connect to it with your device. So if you send it through, you can have multiple subscribers again and they'll get the message. But it's that connectivity to the AWS IoT core that comes out of the box with Amazon FreeRTOS. And as I mentioned earlier in this presentation, it's through a publish subscribe model. So you publish once and you can have multiple subscribers. And in this case, a lot of people were waiting to see if their coffee was ready. So the kettle sends out one update and then that goes out to all the people to say, coffee's ready. And then there's a mad dash to go and get that first cup of joe. And to give you an example of a device shadow, you can see here we've got, in fact, I think we've covered this previously, but to give you a reminder, we've got the desired part here, which is showing you that we want the color to be blue. We've got the reported, which is showing red. But there's one part here, the metadata, which has the timestamp and version, which are pretty important, and I'm sure Avi will cover that later in the presentation. And then we've got the security connectivity libraries. You can see there's a lot of libraries here. It's kind of very book orientated, apparently. We've got the cert-based authentication. So as I mentioned with certificates, X509, this is an example of an actual certificate. I wouldn't try and memorize that. It's truncated, so it wouldn't even work. And this is an example of how you could actually create certificates using the CLI or command line interface. You can do AWS IoT, create keys and certificate. Better yet, you can even specify the output files' names. So in this case, we're calling it certainly.cert.pem and so forth. With Amazon FreeRTOS, there are no open ports, so you only have access to the ones that are secure, and it's secured using TLS. So again, we've mentioned that with 1.2, and you can run code that is trusted. So again, if you don't want people to run unauthorized code or unsigned code, we give you that capability where as long as you trust it, you will run the code. But if you don't have to run it. And you're seeing another pattern here. Over-the-air updates. We have the same kind of functionality here where you can update one device or you can send an update to groups of devices. You can sign the firmware images that you're sending through. So again, you don't run unsigned code or you don't allow clients to run unsigned code. You can stream them over MQTT. As I mentioned, it's a lower payload or smaller payload, and those updates are streamed such that you can get all of them once they're on the actual device and then the update is performed. There's even APIs to help you with installing and rebooting your device because, quite frankly, if you're going to send over the updates, you're going to have some mechanism to not only install it, but reboot it. And again, I always go back to the smartphone example of think about it when you update your phone and then it has to reboot. It's a similar mechanism. And groups. So we've mentioned groups of devices here. You have access to create those same kind of groups so that if you want to run, whether it's updates or decommission devices or perform any kind of action against a group of devices, you have that capability built in. And one of the final things to touch on here is the Device Defender library. So you've got Device Defender. What you can do is you can write policies that help audit and monitor your devices to see that nobody's trying to access them who shouldn't be accessing them, or maybe they're sending data that shouldn't be sent, and you can alert on that. So when you alert on it, you can do it via the regular mechanisms of CloudWatch, and then from there you can use SNS to send an SMS message or an email message. And you can also mitigate on those particular things that are found out. So with the device side metrics that you have access to, whether it's CPU, memory, number of IPs connected, or the originating IP, you can perform certain actions on it. And that means that if an anomaly is detected, you can kind of go in there and say, uh-oh, looks like someone's compromised it, and our device is now a bot and it's trying to destroy the world. We can kind of go in and say, let's decommission that device or kill its certificate so it doesn't do that. But you know what? It's all fun and games until you have a real-world customer example. So I'm going to hand off now to Avi Dubey, who's going to come in and tell you how his team utilized AWS IoT to create an externalized printing solution. So stay tuned.
Thanks, Rudy. I'm Avi. I'm senior developer in Amazon Fulfillment Technology. And today we'll be talking about a specific business problem statement that we solved using AWS IoT. But before we start with the details about the problem statement and solutions, let's introduce what our org does. So our org is called Amazon Fulfillment Technology. The short form is AFT. If I have to explain what our org does in a few sentences, I would say if you think about Amazon retail, whenever a customer places an order virtually on our orders page on Amazon.com, it is this org's responsibility to take necessary actions to fulfill those orders physically. So we have a lot of automation which goes on in our warehouses to manage billions of inventory in order to convert that virtual order which a customer placed into a physical box which reaches to our customers. It's a big domain, but today to keep us focused and very specific to IoT, we'll be talking about printing. We'll define what is meant by printing in AFT, what is meant by external FC, which resulted in a problem statement. We'll go over a solution, what we developed initially using AWS IoT. And then we'll take you through a journey of prototyping to production using AWS IoT Greengrass. So let's start with printing. So when we'll talk about printing in AFT in these slides, we are specifically talking about the business documents, shipping labels, invoices that we print in our organization in order to ship customer packages. Let's go over how printers are working today in AFT. So broadly, if I have to categorize the printers in AFT into two categories, we can divide them into network printers and USB printers. So the primary difference between network and USB printer is that network printers are directly connected to the LAN, while the USB printers are connected to a local compute, which is then connected to a LAN. So in this context, whenever we'll talk about IP addresses or private IP addresses of a network printer, we are talking about the IP address assigned directly to the printer in the LAN. And when we'll talk about the IP address of the USB printer, we are talking about the IP address of the local compute or the local machine it's connected to, which is then connected to the LAN. So today we have these local computes which control USB printers and network printers, and we have browser tools which are used by associates to do printing. All these devices, they are present in FC network. FC means fulfillment center, so we can assume it's a warehouse network. And then we have these cloud servers, web servers, and printing services in cloud service network. I've not mentioned a lot of services here, and we can assume that there's one service which is called printing service, which takes the responsibility of generating the printing document and also sending it to the printers to print it. So today, when there are two networks, the communication happens using a VPN connectivity. So all these networks are connected through a VPN, and hence all these devices, they all are connected to each other using IP address, using VPN, and they can communicate to each other using private IP addresses. So today, when these browser tools scans the local IP address of the printers to print something, this IP address is passed to the web server. From there, it is transferred to the printing service. And printing service uses this private IP address to create a direct TCP socket connection to the printers and the local devices in the FC. And then once the socket is created, then it sends the print documents to these printers. This is all possible. As I explained earlier, they are part of the same private VPN network. so everyone can talk to each other using the private IP addresses. Now let's talk about external FC. So as Amazon's business started growing, we started running into problems related to IP contention. Since all these thousands of devices were in the same network as our services, we are not able to share the same IP address across warehouses because we had to be in the same subnet in many cases. And then slowly the business problem statement related to the warehouse itself started evolving, and we started setting up fully externalized warehouses where every warehouse is in its own private network and not connected through the VPN anymore. So the problem statement started when this VPN connectivity was removed. And this resulted in breaking of two major connections. The first one, where the browser tools were talking to web servers using their private IP address. And the second one was the printing service, which was talking to the devices using their private IP address. So one of these connections, which is the browser to web server, was easier to solve. We externalized those web servers, and hence our browser tools were able to connect across internet. But in order to externalize our devices, we would have needed thousands of public IP addresses, which was not a practical and frugal solution. So we needed a solution for solving the connectivity from printing service to these devices to make our tools work. And the biggest backwards compatibility constraint that we are working on was that there were hundreds of existing tools which are still going to pass these IP addresses of the local devices, that is the private IP, to the printing service via externalized web servers. But now printing service has to use the same IP address to create the same kind of communication across internet, which is not possible if we just rely on the private IP. So let's start with how we started thinking about the solution. So we initially took the USB connected printers. Since they were already connected to a compute, we installed the IoT SDK on them. And as soon as we got that IoT SDK, we had a duplex communication using MQTT protocol, which Rudy explained earlier, via IoT. And now, in order to keep the mapping, we created a mapping between private IP address of the device or the printer with the unique thing name of IoT. But since this IP address can be used by other warehouses also, we had to add some additional mapping. So in our case, we used the business tenant ID, which was unique, like AFTX means AFT external. Plus the indie one is something like a warehouse name, which the combination of business tenant, warehouse ID, and the private IP address made this key globally unique, similar to thing name. And now with just by IP address and combining the other two things, we were able to reach out to your unique thing name and to the device. So now the solution worked like this. The browser tools were calling our external web services. Web services are calling printing service. Printing service used to do the lookup using the IP address along with the business tenant ID, warehouse name, get the thing name, and send the document to the local printing device. Once the document reached the IoT SDK, we had a local function which was sending the print documents to USB printers. So this was pretty straightforward. And then we had to move to network printing. So in network printing case, we had IoT SDK, but we didn't know where to install this because there's no local compute like USB printers. So initially we thought, why not make all the network printers smarter? That is, buy some local computes like Raspberry Pi or any cheaper solution and connect them to the network printers and install IoT SDK on those devices and connect them to IoT. Yes, this would have worked, but at a scale of Amazon, when we are talking about thousands of devices, we're also talking about thousands of new devices, and it's a very non-frugal solution. More than the cost of the devices, it's the cost associated with managing these thousands of devices. These are new non-standard devices in the operations world. So instead of going ahead with this approach, we already have a compute, and the compute is the machines which are controlling USB printers. They are sitting in the same network where the network printers are. So why not just reuse that compute to proxy the same IoT commands or IoT packets for the network printers also. And we went ahead with this approach. So, and this was a very frugal solution where we didn't have to spend anything. We reused the existing compute solutions, which are already present in the operations, to also control the network printers along with the USB printers. So this was a story for our initial solution. It was a prototype up and running. We had a solution, but there's an interesting image which I've shared. So there are two coffee machines which are shown here. On the left side, there's a pressure cooker with a safety valve which is sealed by a screwdriver. Yes, there's steam coming out, froth is being generated. Yes, it makes a coffee. It works. This is how our solution was initially. It used to work, but there were a lot of cases which has to be considered to take it to production. Because once you talk about a production solution which is going to power your business, it's a completely different story as compared to prototyping something. So initially we started with writing a list of features that we need in order to convert our prototypes into production solution. For example, some of the features which I can explain here are multiple platform support of the edge devices. Some were Linux, some were Windows, some were local computes like Raspberry Pis or non-standard devices. We had to find a solution for packaging our code because our code is not going to live on the edge devices. We had to manage the lifecycle, phase deployments, rollbacks. These are all edge compute devices, so we need a solution to automatically provision them and convert them into IoT devices. Since we're talking about backwards compatibility, since we had to also think about providing blocking/synchronous APIs to existing tools, IoT does not provide any such synchronous API solution using MQTT topics, so we had to think of such solution. Sequencing of commands is very important in printing world, and with IoT involved, sequencing is not that straightforward. Then we are talking about now using the same edge devices, which was earlier controlling one USB printer, to control multiple network devices. If the device goes down, we didn't want to bring all the network printers down. So we had to think about automatically failing over a particular device if it's offline and using some other compute which is online to control the network printers. Print adampancy, basically some way of making sure that the same document is not printed multiple times. Large printing docs basically means the documents which are larger than 128 KB size limit of the IoT. So we had to find a solution about that. And monitoring, alarms, those are the regular things. So for today, for the sake of this conversation, we'll only cover the top 4 topics and explain how you solve those problems to productionize our solution. So let's start with the first one, which is multiple platform support, standardization of code packaging, phase deployments, rollback. This is where we used AWS IoT Greengrass. So we installed Greengrass SDK on these edge compute devices, which provided us with multiple platform support and also provided us a way in which we can now deploy our Cloud Lambda functions packaged with all the dependencies on the edge devices. And we can actually host our logic on these Lambda functions to control USB printing, network printing, and any other thing what we want. We built our printing API using completely serverless technology, using API Gateway, Lambda, DynamoDB, transferring the control to AWS IoT Greengrass, IoT topics. These Lambdas were subscribed to the IoT topics, and we had an end-to-end solution which was pretty standard, and it provided all the functionalities which we developers are used to when we deal with EC2 machines in AWS. Let's talk about the provisioning solution. So since these devices were already existing, they were not owned and manufactured by us, we needed a way to automatically provision them. At the same time, we needed a way to authenticate and authorize the provisioner so that not anyone can provision these devices. So we were not able to use the standard GITR and GITP solutions because the whole manufacturing is not controlled by them, the initial root CA, cannot be distributed on the fly to external warehouse owners. So we reused our own solution for the provisioner. So initially we authenticate and authorize the provisioner and generate a temporary credential, which is then given back to the provisioner, which allows temporary access to the cloud resources. And our script allows the provisioner to provision the devices in cloud. So using this temporary key, we create the Greengrass course, Greengrass certificates. We create the IoT topics to which the local lambdas will be subscribed to. IoT Greengrass also creates a unique device certificate, which we transfer back to the provisioner, which is then transferred to the device which is being provisioned. And then we automate it further where we download the Greengrass software, we start the daemon, we keep the daemon in a specific path so that even if the device restarts, the daemon restarts. And as soon as daemon is there, we have a duplex connectivity. And with this, we can even call Greengrass APIs to install the Cloud Lambda functions on the edge devices. And once the Cloud Lambda functions are installed and they're running, we can control the printers across internet still using their private IP addresses because we are using IoT to transfer the packets through the internet. Let's talk about synchronous and blocking APIs. So as discussed earlier, we had to provide a backward compatible solution where our tools were already expecting some synchronous APIs. So in this case, when clients were calling our Cloud Print API, we used to publish, and so we used to subscribe and wait with a particular timeout on a unique IoT topic using MQTT. And then we used to transfer this unique IoT topic to a command topic, which our local lambdas are already subscribed to as part of the initial provisioning. When Lambda takes the printing action or other actions and it needs to reply back, so it publishes its result of the action on this unique topic, which it was sent to, and our Cloud Lambda is waiting on. And as soon as we subscribe and our results are available, we stop the timer and we return the results synchronously back to the client. So clients did not, in our case, come to know that, yeah, it's actually a asynchronous protocol which we are using in the backend. They got the same experience as they have today in the synchronous world. There are a few things which you have to keep in mind with the payload, or maybe you can have your own unique solutions. For example, in our case, we use unique reply topics so that the replies of a particular command does not get mixed up between Lambda functions if multiple Lambda functions are trying to print on the same device. Similarly, we had a thing called command time to live so that if the device goes offline and it will still receive a command later because we use QoS 1, but it can ignore it if it knows that it's coming from, it's like a stale command which was initiated 5 or 10 minutes back. We use things like command trigger time to track the end-to-end latency as when the command initialized from the print API and at what time it reached. And the other thing which we have to keep in mind is the MQTT client, which we create to subscribe. So it's not recommended to create a new subscription on every single request coming. And in our case, we create a subscription per Lambda container, and we keep that subscription throughout the lifecycle of the container. Let's talk about the sequencing of commands. So Rudy mentioned about IoT Shadow, but there was a very specific thing which I would like to mention here, which is called version. So borrowing some things from his document, this is the most important thing which really helped us in figuring out the sequencing problem. So this version actually acts like a record version number in databases where you can update something and it automatically bumps the version number. So two different callers cannot update the same document at the same time. Now let's see how we use this to get a sequencing of printing commands. So when print API is called, we update the shadow, the desired section of the shadow with a thing called print docs, It's like a array you can assume where we say, hey, print 1, 2, 3, 4. These are the 4 documents printer has to print. Let's say we started with version 1. When the local edge compute device receive this shadow update, they will do the printing and they'll update back the document by removing the printer commands which they have already printed and updating with whatever is left. For example, the device, the local lambda was able to print only document 1 or 2 for some reason. It will update back the shadow saying, hey, I've removed 1 or 2, 3 and 4 are still remaining, and this is the latest update. And the version number 2, if you look at it, it's getting updated automatically. Now, if someone wants to resend or add more documents for printing, they have to read before update because of the version number. Let's take another sequencing where it gets interesting. So let's say Cloud Lambda sent 4 documents for printing. While the local Lambda was doing printing, it got the version 2. There were more updates sent for the printing. Now 2 more documents were added to the printing because the other Lambda, it read the version number 2, updated the document with version 3, and it's a valid update. Now when local compute will try to update, it will not be able to update because it has not the latest version. So in this case, we use the local Greengrass storage, which is provided by Greengrass, to check how many documents we have already printed. And this information becomes useful if we see the flow after this. So let's say the initial call to cloud failed from the device regarding update. It will sync and it will update saying, hey, I have printed all the 6 documents. Let's update print document with empty array. But there's one thing to notice here that let's say this Lambda was able to print 1, 2, 3, 4. And it tried to update back and it was not able to update with version. Since there were 2 updates on the same shadow, there will be 2 different subscriptions which will trigger the Lambda twice. So even in first case, if we updated 1, 2, 3, 4 and the version number failed, we can actually safely ignore and wait for the second update to the local device Lambda. In that case, you will receive only 5 and 6 and we can do the printing and move on. And even if we receive, let's say 1, 2, 3, 4, 5, 6, since we are storing what all things we have printed locally in the Greengrass local storage, which can actually share across Lambda instances, we can actually ignore the documents which we have already printed and move on with the remaining documents. One thing which we have to keep in mind here is that the local Lambda, it's running on an edge device, so maybe the device can go offline for some time. And then when the device comes online, maybe it can receive more commands saying print more documents. If it remembers what document have already been printed across Lambda instances, it becomes really helpful to avoid printing duplicate documents. So these are the 4 main things which we wanted to share where we had to dive deep to create our solution in a production environment. With IoT, we would suggest a lot of things you have to keep in mind if you are trying to productionize your solutions. There are amazing AWS documents and examples around all these concepts, but these are the key ones which I would mention as a suggestion. For example, you have to understand the QoS concepts. MQTT supports QoS 0, 1, and 2. IoT supports only QoS 0 and 1. So what are the impacts of that on your design? You have to be careful with the ordering of connect and disconnect events coming and generating from IoT. There's a good solution and good recommendation on the AWS doc around how to handle out of order events. Because if we don't handle that, you may mark a device offline even though it's online. Then the next thing you have to keep in mind is what is meant by Greengrass deployment being success. Does it mean that your Lambda has been deployed and it's running successfully or something else? So Lambda has been deployed, but I think you have to think of these things just like how you think of you're deploying your software in EC2, where you check whether your functions or the service is actually deployed properly and running as expected or not. Then you have to think about, let's say you have deployed a few Lambda functions. What if you have to deploy new Lambda functions on the edge devices because of some new use cases? What should you do, or what you can do in those cases? Uh, Greengrass can be used in two modes, containerized and non-containerized mode. Both have their pros and cons, and they come with their own features. So again, pick as per your requirements. And then on-demand Lambda gets interesting. So we used on-demand Lambda, but you have to think about things like, if it's on-demand and a Lambda instance is busy, a new Lambda instance will be created for you. But if a new Lambda instance is created, how do you control how many such instances are created on the fly, where you don't end up utilizing all the resources of the existing edge compute devices? And this is all we had to share with you today based on our learning and experience of developing productionized solution at Amazon scale using AWS IoT and Greengrass and other serverless technologies. For the resources, you can refer to the links provided in the slides, where there's an AWS IoT workshop, which Rudy has helped us create, where you can go through AWS IoT code, Lambda, SNS, and other things. It's primarily focused on IoT. And then we have another link where you can see a live demo of an application which was built using AWS IoT. That's all from our side. Thanks a lot, Rudy, for joining us and on this presentation. And I'm Avi. Thanks a lot. Bye-bye.